Today we're going to use algebra tiles to illustrate several concepts about arithmetic and algebra. Let's start by adding and subtracting integers. A small green tile represents positive 1. A small red tile represents negative 1 or minus 1. What is 1 minus 1? 1 minus 1 is 0. 0 is the integer which is neither positive nor negative, so we have neither red nor green. Let's use our algebra tiles to show an addition problem. You can follow along by drawing algebra tiles, or you can cut some out of paper to play with. Let's try the problem 3 plus negative 4. We'll start with 3 green tiles, positive 3, and add 4 red tiles, negative 4. The red tiles and the green tiles cancel each other out, and we're left with one red tile. Positive 3 plus negative 4 equals negative 1. We can also show subtraction with our algebra tiles. Let's think of our addition problem in a different way. 3 plus negative 4 is the same as positive 3 minus positive 4. How can we take 4 green tiles from 3 green tiles? It seems we need one more green tile. We can use the fact that a green tile plus a red tile equals 0. Let's add 0 in the form of one green and one red tile. Now let's take away our 4 green tiles and we're left with one red or negative 1. Multiplication and division can also be shown with algebra tiles. Let's model 4 times negative 3. 4 means 4 groups, and negative 3 means 3 negative or red tiles in each group. We can see a total of 12 red tiles, or negative 12. Let's try a division problem, negative 12 divided by 4. This means to take 12 red tiles and divide them evenly into 4 groups. In each group, there are 3 red tiles. Negative 12 divided by 4 equals negative 3. Let's try one more. Negative 12 divided by negative 3. Here, it might be helpful to think about the fact that negative 3 is the opposite of positive 3. This means take 12 red tiles and divide them evenly into 3 groups. There are 4 red tiles in each group. Since we're dividing by negative 3, we take the opposite of a group. If we take the opposite, each group has 4 green tiles. Negative 12 divided by negative 3 equals positive 4. Now we can use our tiles to represent operations with variables. This longer tile can represent the variable x. Green represents positive x, and red represents negative x. A green and a red x tile cancel each other out. The area of the large tile is x times x, so this tile can represent x squared. Remember that the shape of our tiles is not proportional. We can't fill an x squared tile exactly with x tiles, or an x tile exactly with 1 tiles. Now we can model a polynomial. These tiles represent x squared plus 2x minus 3. We're going to add x squared plus 2x minus 3 to x squared minus 3x plus 4. Remember that a red tile cancels out a green tile. Our new polynomial is 2x squared minus x plus 1. Let's use algebra tiles to multiply two binomials. We'll multiply x plus 2 times x plus 1. X plus 1 times x plus 2 go along the top and side. X times x is x squared. X times 1 is x. X times 2 is 2x. And 1 times 2 is 2. So we have x squared plus 3x plus 2 as our product. Let's try division or factoring of a trinomial with algebra tiles. We'll try factoring x squared plus 5x plus 6. First, we fill in the area of our rectangle with our trinomial. The area of a rectangle is length times width, so we count the length and width of our rectangle to factor. The area is x squared plus 5x plus 6. Along the top and along the side, we'll count our factors. On the top, we have a length of x plus 3. On the side, x plus 2. So our factors are x plus 3 and x plus 2. Let's solve this equation. X plus 2 equals negative 2x plus 5. X plus 2 equals negative 2x plus 5. Add 2x to both sides of the equal sign. A positive x will cancel out a negative x. Now subtract two ones from both sides of the equal sign. A negative 1 cancels out a positive 1. We have 3x equals 3. Divide both sides by 3. For every x, there's 1 1. So, x equals 1 is a true equation. Algebra tiles are awesome. In conclusion, we've used algebra tiles to model operations with integers, operations with polynomials, and solving equations.